Hey guys, hope you're all doing good and welcome to a new video. So in the last video I forgot to mention an important thing, which is the computational mesh size. So in this particular case what I'm doing is I'm basically starting up with a mesh size of 0.012 and what I'm doing is I'm adding a fixed embedding which is of scale 2. So how do I go about all these things? Well, the answer is quite simple. So whenever you're running a simulation, right, you basically need to look for the minimum flow path, right? So in this particular case, you can kind of see that the gap between, say, this part and this part, that is kind of the smallest flow path that's available, right? So what you can do is you can just measure distance, and you can basically select this particular vertex and this particular vertex roughly and click on apply. So you can see that that's about 2 millimeters, right? So here our base grid size is 12 millimeters, right? So what you can basically do is open up your calculator. So you have 12 millimeter cells and you roughly want 2 millimeter cells, right? So that basically means that you need to refine the mesh in that particular area by a factor of 6. So what I've done here is used fixed embedding, and I basically refined it using an embed scale 2, which makes my mesh 4 times smaller. In other words, according to my setup, I will basically have the cell size there as 3 millimeters and not as 2 millimeters. So is this okay? Well, according to Converge, it should be okay. So if you remember, we talked about something called a cell pairing, right? So whenever you have this larger cell and if it is being cut and if the volume of the cut cell is less than 30%, then that's basically bad because that cell gets paired. Right now, in order to avoid cell pairing, we need to make sure that our cell size is large enough, but it's not that big so that it causes cell pairing. Well, in our case, we have a 3 mm cell in a place where there's only 2 mm gap, but that's fine because when the cell is getting cut, its volume is going to be 60% of the full cell volume, which means it's not going to get paired. In other words, we are still going to have one whole cell in that particular gap. Now, if you ask me if that's okay, well, it's not. So that is why what I've done is I've basically set up another simulation, and in this particular simulation what I've done is I've made the base mesh small. In fact, I'm going to 0.01, which is basically 10 millimeters, and then I've used fixed embedding where I'm going to a scale of 3. My cell size in that particular area is 1.25 millimeters. This means I'm going to have at least 2 cells in that small gap. Now, whenever you're setting up a simulation, this is how your thought process should be. The mesh size cannot be set up in a random fashion without any thought process. If you do so, majority of the time your simulation is going to fail. Always apply some type of engineering judgment to calculate what your mesh size should be, at least for a starting point, and then refine it from there. So in our case, we have both of these two simulations, and what we are going to do is we are going to run both of them. Now in our case, we have both of these two simulations and I've already run them. So let's kind of take a look at some results. So what I've done here is this is basically Sigwin, and if I open up the log file, and maybe let me just open up the last 20 lines. So you can see that this particular simulation, the coarse mesh simulation, it ran for about 26,000 seconds. That's a lot. That's close to, say, 8 hours, right? Now we are talking about the coarse simulation. Now, what about the fine simulation? Well, there the story is much more crazy. You can see that the simulation started on September 21st at 1935. And if you look at the simulation end, right, that's September 27, right? So that's a huge simulation, right? So it's running for 6 days and the simulation is not complete. I ran it only till 1.4 e minus 1 seconds because the simulation started get converged results. So how do the results look like? Well, for that I made a couple of line plots. So here the first plot that we are going to be looking at is mass flow rate, and we are looking at mass flow rate as a function of time. So first of all, you can see that when you run the simulation for about 0.14 seconds, in the refined case, the simulation has already reached a steady state. And if you look at the case, we did not run it long enough. We ran it only for 0.06 seconds approximately. And you can see that for mass flow rate, the answer is matching pretty well, right? Now this is mass flow rate at the inlet boundary where you're provided pressure condition, correct? Basically saying that we're kind of getting the same mass flow rate. Now the second plot that I want to look at is the total pressure at the outlet. Now this is basically the work which is being done by the pump at the end of the day. So notice how close the results are between the coarse and the refined case. The coarse case just took 9 hours, whereas the refined case took close to 6 days. Now remember, we are running the refined case for much longer, so the comparison is not exact, but it kind of tells us that if you are looking at fundamental quantities like pressure drop and mass flow rate, you don't have to go too crazy on the computational mesh size. However, if you want to simulate key events like cavitation, and if you want to capture, say, events like slippage, then you might have to add more computational cells in that small gap. Alright, so now let's take a look at some post-processing results. So I have ParaView here. So this is basically for the coarse case. So I'm going to just deselect some data here, and right off the bat, what I want to do is I want to create a cut plane, and let's create a cut plane along the Z normal, right? So that seems more appropriate, and I'm just going to drag it and kind of cut it in the middle, and I'm going to click apply. I think a good location to be. So maybe just drag it a little bit more. Okay, that's fine. So now what I'm going to do is I'm just going to hide the plane, and the first thing I want to do is I want to look at the pressure variation, right? So let's go to the colors, and I'm going to click on pressure, right? Immediately you see that the pressure is all just a single color. Well, that's because we are at the 0th time step. So let's go to the final value here, and then I'm just going to click on this reset button, and there you go. You can see that at the eye of the impeller, that's where the lowest pressure is, right? So that kind of makes a lot of sense, right? So that is where the fluid is basically coming in, and because of the impeller spinning, it creates that nice low pressure area, and that is what helps the centrifugal pump suck more fluid, and it basically gets pressurized, and as it goes outside, you can see that there is this diffuser like section. So if I put it in Z normal, you can see that diffuser like section where the area of cross section increases, which basically results in additional increase of pressure. So that basically looks good. So how about velocity? So let's take a look at the velocity, and that also looks pretty good. You can see that there is this separation area, right? So what's happening is the flow spins, and as it exits, there is this particular corner where the flow starts to detach. Now this means that your outlet boundary conditions are not that super accurate, right? This is basically a problem. Why is that? Well, we were basically saying that at the outlet our mass flow rate is fixed, correct? But in these type of scenarios, what's happening is you're encouraging reverse flow, which means technically flow can actually recirculate. So in other words, flow from the outlet can come back in, which is called as backflow. So what do we do in these type of situations? Well, to start with, it's a bad idea to basically place the boundaries so close to a separation bubble. So what's going to happen to this particular flow pattern is, if you actually extend this outlet, then this flow that gets separated is going to reattach, and then you will have smooth flow through the outlet, right? So when you're running CFD simulation, if you have to get accurate results, then you need to make sure that in the location of boundary condition, the boundary conditions are actually valid. In this particular case, it's not, because there is flow reversal, which means in order for the mass flow rate to be achieved, you can actually have excess mass leave from the top area so that the net mass flow rate is equal to your boundary condition. In other words, the equations are working in your favor to reach the boundary conditions, and that shouldn't be the case. Ideally, you need to have a condition where you have the boundary condition, and when the flow is being calculated at the boundaries, the solution naturally reaches the boundary condition value. Now, the reason why we ended up doing this simulation is to make this important point. So whenever you are situating boundaries, make sure that you put them in a location where the flow is not reversing or recirculating. Alright, so this flow pattern looks okay to me. So you can see that away from the impeller, that is where the maximum velocity occurs, because the linear tangential velocity in that area is going to be r times omega, and since r is maximum at the tip of the impellers, that is where the maximum velocity is going to be. So that checks out. So the next thing that I want to do is create a vector plot. So I'm going to use the glyphs, and I'm going to be using it for vectors, and I'm going to apply. And this looks kind of cramped, so maybe what we can do is we can reduce the number of samples to 1000, and I'm just going to scale them a little bit. Alright, and what I'm going to do is I'm just going to color it by black color so that you can see the vectors very nicely. And this is exactly what I'm talking about. So if you look at this particular area, you can see that there is flow reversal, right? And we are saying that the boundary condition there is constant across the face. Again, the reason why I'm repeating myself is because this is an important point, and make sure that you remember this. Alright, so overall our simulation setup looks pretty good. Qualitatively, we are getting very nice results. The flow is taking place in the right direction, pressure is increasing in the right direction, and the simulation has reached steady state. So this means this would be an excellent setup or computational model for this particular pump, So what we can do is we can actually run performance curves. So what we can basically do is we can take this particular computational setup and we can keep on refining it if required. Alright, with that I would like to conclude this video. Now this tutorial is basically part of your project, so make sure that you set it up correctly. Thank you. Bye.